So for chapter 53, unlike the other chapters, we're not going to cover every single section in that chapter. So this chapter is only going to cover sections 1, 2, 3, and 6. So numbers 4 and 5 are not going to be on your exam. So the first section of chapter 5.3 is going to look at population density and dispersion and demographics. So what is a population and how do we study it? Population is a group of organisms of the same species that live in the same general area. Typically, we define a population as a group of intermating individuals within a single species. So the person who is studying a population as a scientist gets to decide where the population kind of starts and stops. Sometimes this is really clear because they have a specific natural range and they don't go outside of that. Sometimes if the animal is highly mobile, that's not very clear, and a scientist has to kind of say, I'm going to stop studying the population here. True kind of defining outline of where a population starts and stops is defined a little bit by how humans study populations. So a population has two general characteristics that we like to look at and characterize when we study a population. The first of those is density. And density is how many of something fit in a specific area. So as a scientist studying a population, we have to determine what the border of that population is to determine the density. We need to know where they live. So this area is the habitat. And if this is really big, it might be fairly not dense because they might be very spread out. If the habitat's very small and there's a lot of individuals inside of it, it might be a very dense population because they're all clumped together. So the density is the total number divided by the area. The other component that we look at is usually the dispersion. So this is the pattern of spacing. So are they clumped up together in one spot, or are they spread out equally, or are they kind of spaced randomly? So this is basically asking, how do they fill the habitat? So there's a couple of different factors that go into population density. The first is the habitat. So we have to determine where these live. So for example, this is a bird species. A bird species is probably going to have a larger habitat than something that's terrestrial and doesn't move around a lot. So the bird scientist who's studying this bird would have to go out in nature, observe these birds, figure out where they actually live to figure out the area that they live in. And then the actual number of birds depends on a few different things. We have two different things that add birds to the population. So when birds are born, they get added to the population. And when birds immigrate. So this could be birds coming from a different population to this population. So this is an influx of individuals. This is typically the same species, just from other areas. So maybe someplace that the scientist would have determined was a different population. So this is the active population that we have here. And then there are a couple of things that will remove individuals from the population. So the number of deaths, right? This is going to remove individuals. As a bird dies, it gets eaten by this hawk up here. Or emigration. This is when they leave to go to a different population. So these individuals might leave to go live in a different population with other birds. And so we do calculations and do look at growth curves of births and deaths, as well as immigration and emigration, to determine the population density of species. We often can't go figure out the exact total number. So when we sample a species, it's really hard to go to an area and actually count every single individual. We don't have the time or the money or the resources in science to be able to do this. So often when we are going to look at population density, we're going to have to estimate. So what we'll do is we will count the number of individuals in a small area and then assume that that's about the same for the entire area, and we will extrapolate. There's a couple of different ways of doing this. We can do random sampling, so this is on land. One thing that you can do, let's say I wanted to count the density of these yellow flowers, you can take this big, probably 1 yard by 1 yard square, and these are often made of just like PVC or anything, and go out into the population where these flowers live. And you typically throw these units around randomly. There's lots of different theories for how you should sample, and you would count the number of yellow flowers inside of this 1 by 1 meter square. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you would sample this a whole bunch of times throughout the entire population's area, and then come to some kind of average and determine the population density based on your sampling and assume that it's the same throughout. Another method of extrapolating is the mark recapture method. So this is, in case you don't recognize me because we're online, this is actually me as an undergrad with blonde hair. This is my undergraduate research mentor, Dr. Grubbs. He's at FSU. And we were catching sharks. So right here, this is a tiger shark. And then this is a black tip. And you can see that they have these little spaghetti tags right there. And so what we would do is we would catch the shark, measure it, take all sorts of information about it, GPS, everything, and then tag it, and then send it out. And then if anybody catches this shark again, so that's the mark part, was us tagging it. The recapture part was waiting for some other scientist to catch the same fish, bring it up, see the spaghetti tag, and call it in. And so what they would do is they would send in that data to us, the researchers, and we would note that that shark got caught again. And there are complex equations that estimate, based on the number of sharks caught and recaptured, how big that total population is. The other hand is dispersion. So dispersion is how are we spread out. So there's generally 3 main patterns of dispersion. Clumped. So we can see here that we have individuals that are clumping together. And this usually happens where the resources are in small areas. So they're going to clump around shared resources. So this might be on a coral reef, and the starfish are going to clump up where they have patches of mussels here to eat. Another one is uniform distribution. So uniform is pretty much where there's about the same distance between each individual as every other individual. And so you can see here that we don't have any clumps really. They're all kind of spread out about the same. And this happens typically when there's lots of competition. And that might be competition for space usually. And that's gonna, so these penguins all have their nests, and they all want their own space for their nests to brood their eggs. And that's going to prevent them from coming too close to each other because they don't want to damage each other's, they don't want to damage their offspring. And then random is kind of somewhere in between. Often we see they're kind of spread out in places, and then in other places they're pretty clumped together. Random dispersion is often going to happen when natural things are just going to cause the dispersion. So in this case, we've got flowers that are randomly dispersed by wind. And it might be the wind is blowing pollen one way one day, and it blows it another direction another day, and we end up with maybe clumps in 2 different places. So within a population, we want to study how these effects change over time often. And so to study the vital statistics, so how populations change over time, that's a population metric called demography or demographics. And you might have heard the term demographics talking about things like the census. And the census is absolutely just a population study of the humans on Earth. And they're taking your age and your weight, like your job and where you live and that kind of thing. So a lot of times when we look at animals, what we like to look at is their reproductive rate and their survival rates, because those are going to tell us how many births there are and how many deaths there are. So this is something called a life table, and a life table is typically going to only look at females. So for example, this is only looking at female ground squirrels here. And this starts as a cohort. So there were 653 ground squirrels born 1 year. And what happens is every year they come back and they count the number of ground squirrels left from this original 653. So 653 is 100% of the population. And then every year when they count the number, we can figure out how many died. And this is usually only going to look at females and then the number of female offspring. And the only reason we look at females is because we don't want to count individuals twice. So females are going to contribute to the next generation by having babies, and we know we can count exactly the number of offspring each female has. It's hard to determine how many offspring a male contributes to because we don't know who the female mated with. So a lot of the times we just count females and we don't use males at all in these life tables. The life table is a little hard to picture. This is really great if you're into data analysis, but looking at this as a trend is a little difficult to see. So what we do is we take the data in a life table and we make it into a graph called a survivorship curve. And there are 3 main types of survivorship curves, and I would highly expect that you are going to see this kind of curve on the exam, so you should know these 3 types. So type 1 is like us. So these are going to have really low death rates early on in life, and then the death rate increases as we get older. So this is not 100 years, this is 100% of your lifespan. In humans, that's somewhere around 80-ish years. So let's assume that the number of survivors, let's start with 1,000 people, right? So over our lifetime of 1,000 people, once we hit 50%, so that's about age 40, most of those people are still alive. And then as we get into our 60s, 70s, 80s, we see that the number of people drops off precipitously. So there's a low percentage of death here and a much higher percentage of death at the end of this life curve. The opposite of that is type 3. Type 3 is going to have a very high death rate right here, high death rate at the very early part of the life, and then it kind of stabilizes off here, and then there's a pretty low death rate at the end here. So this would be something like, this is a mussel. Anything that uses the mechanism of making tons and tons of offspring just in hopes that one will survive. If you think of fish, typically this is how fish would reproduce. Fish will just put their eggs and sperm out into the water and allow them to fertilize, and they make hundreds and hundreds of eggs in hopes that a few of them will survive to kind of this point and then make it throughout the rest of their life. Humans, on the other side, put a lot of care on the front end, right? We nurse our babies, we have our children in our homes until they're 18 plus, until you're adults, and then that ensures that most of the children born survive to adulthood. Type 2 is kind of in between. This is where they have a constant death rate, so the death rate stays the same throughout, and it creates kind of a linear curve down here. This is a little less common. Most species will either use type 1 or type 3. So these survivorship curves pretty much are only looking at the number of individuals that are dying, and so we can look at individual death. The other hand to this equation is how many are born, right? Because that's going to be the number of individuals added to the population. So in addition to looking at death, we usually look at reproductive output, and we're pretty much usually going to look at females and then the number of females that are produced. Different species reproduce at different ages, so it doesn't make a lot of sense to put them on kind of a graphic like we did the life curves. So every species is going to have a different reproductive age where they are able to go through sexual reproduction like that.